Welcome to the last lesson on non-Euclidean geometry. In this lesson, I'm going to talk about elliptic geometry. As I mentioned previously, elliptic geometry is an example of a geometry in which Euclid's parallel postulate does not hold. There's two different variations, and I'll talk briefly about both of them in this lecture. One is called double elliptic geometry, and the other one's called single elliptic geometry. In the double elliptic geometry, each pair of lines intersects in exactly 2 points, and in single elliptic geometry, each pair of lines intersects in just 1 point. In both types of these geometries, straight lines are finite in length. We'll see that when I show you the model. There's a complication here beyond what we have in hyperbolic geometry. And if you recall in the lectures from hyperbolic geometry, we negated the parallel postulate, and we were able to make use of propositions 1 to 28 from book 1 of Euclid's Elements, as well as some other propositions from Euclid's Elements that did not depend on the parallel postulate. Unfortunately, there's no such simple approach for elliptic geometry, since the axioms used in proving many of the first 28 propositions in Euclid's Elements involve assumptions that do not hold in elliptic geometry. So in the interest of simplifying the introduction here, the axiomatic foundations for elliptic geometry are not discussed. For the interested reader, I have a couple of references here. Chapter 7, Section 7 of Gans provides an axiomatic presentation for double elliptic geometry. And Chapter 8, Section 4 of Gans provides an axiomatic presentation for single elliptic geometry. There's also a more technical discussion of axioms for elliptic geometry in the article Axioms for Elliptic Geometry. So I'll give you these references in case you're interested. It's a bit more complex than hyperbolic geometry, which kind of flowed fairly easily from Euclid's Elements, with the one exception of negating the parallel postulate. So I decided not to go into these. It's a rather complex set of axioms, but again, if you're interested, I'll give you some references. In lieu of an axiomatic development, we'll discuss specific models for elliptic geometry. We'll have a spherical model for double elliptic geometry, and we'll use a hemispherical model for single elliptic geometry. We also wanted to mention that the term elliptic is a bit of a misnomer, and I have a quote here from a book by Coxeter. Let me just read that off. The name elliptic is possibly misleading. It does not imply any direct connection with the curve called an ellipse, but only a rather far-fetched analogy. A central conic is called an ellipse or a hyperbola accordingly, as it has no asymptote or two asymptotes. Analogously, a non-Euclidean plane is said to be elliptic or hyperbolic according to as each of its lines containing no point at infinity or 2 points at infinity. So even the explanation is a little bit cryptic in terms of how the term elliptic got there. So again, it doesn't have to do with an ellipse. I guess that's the main point. And what follows, we'll have descriptions of two models, as I mentioned, for elliptic geometry, and I won't be giving any proofs, or at least for most of the things. I believe I did have one proof in what follows. In the spherical model of double elliptic geometry, we use the surface of a sphere as our model, and all the points on the surface of the sphere constitute the points of our double elliptic geometry. Lines are represented by something called a great circle. I've shown two here, A and B, and they're circles that have the same diameter and same center as the sphere itself. The term great circle is used because you could have smaller circles on the surface of the sphere. They're still circles, but they're not representing straight lines in this model. The straight lines, being great circles, are of closed curves of finite length. If the radius of the sphere, and thus the radius of each great circle, is r, then each great circle, and therefore each straight line, is of length 2 pi r. Two great circles meet in 2 points known as antipodal points. So we see here our great circles A and B meet at points P and P prime. And that's true for any two great circles. They always meet at antipodal points. So that's the model. It's fairly simple. I have a little bit more on this in the next few slides, but the model itself is simple. So you have lines being these great circles. You can still have smaller circles, or you can have ellipses on the surface of the sphere. Points are just points on the surface of the sphere, and then we have this new concept, antipodal points. They're on opposite sides of the sphere. We have a few more facts about straight lines on this slide here. I already mentioned two great circles, or what are straight lines, meet at antipodal points. So we have A and B meeting at P and P prime. If you have non-antipodal points like R and Q, then there's only one straight line, in this case A, that goes through both of those points. And we have one other fact. Through each point there pass infinitely many straight lines, the totality of which covers the entire sphere. So you may want to try to visualize that. Just pick point P here and just imagine all the different great circles that could go through that, and clearly it'll cover every point on the sphere. The shortest path on a sphere joining one point to another is called a geodesic arc. So for example, R and Q are joined by this arc here going through P prime. That's known as a geodesic arc. For non-antipodal points, there's also a second, longer path. So in other words, that would be the path going from Q to P and then around R. But this path is not considered to be a geodesic arc. In the case of antipodal points, there are two shortest paths. That's clear. So if you have P and P prime, you can either have an arc going that way or an arc going that way, and they're both the same length, and they're both known as geodesic arcs. A geodesic arc is always an arc of a unique great circle. A geodesic arc is the analog of a line segment in Euclidean geometry. The distance between two non-antipodal points on a sphere is defined to be the length of the geodesic arc joining them. So in other words, the distance between R and Q is the distance of this arc. If two points are antipodal, then the distance between them is half the circumference of the great circle. So if the circle and the sphere have radius r, then the distance between antipodal points would be pi r. We have one theorem here, I believe the only theorem in this lesson. 3 points on a sphere necessarily lie on the same great circle if two of them are antipodal. And the proof is kind of simple. There are an infinite number of great circles with the same two antipodal points. We mentioned that earlier. It is just a matter of selecting the great circle that contains the third point. Then from this theorem, we have another concept. Consider 3 distinct points not on the same great circle. By theorem 54, each two of the points must be non-antipodal and lie on a unique geodesic arc. If A, B, and C are 3 points on the sphere, then the distance A to B plus the distance B to C is greater than or equal to the distance from A to C. And if A, B, and C are on the same great circle, then we would have equality here. And this is known as the triangle inequality. We've seen that before. The sum of the angles of a spherical triangle is greater than 180 and less than 540. You may want to think about triangles on a globe to kind of get a sense of why this is true. Two spherical triangles are said to be congruent if their corresponding sides and angles are equal. However, the angle-angle-side congruence doesn't hold necessarily for spherical geometry. And there's an example here. I'll give you the link to it. See case number 5 in the oblique triangles section of this Wikipedia article. I'll give you a reference in the information to this video. The other triangle congruence principles do hold true. That would be side, 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 angle, side, angle, side, angle, and angle, angle, angle. But angle, angle, side doesn't work. The area of a spherical triangle is given by this formula here, r squared times the sum of the angles minus pi, where r is the radius of the sphere. For a right triangle, and I've shown a picture here of it, we have some formulas. They're known as Napier's rules for right spherical triangles, and won't read these off, but I'll just show them to you here. So these are all for alpha, which is opposite the right angle, and you can have similar formulas for beta. Or further, it's possible for a triangle to have 0, 1, 2, or 3 right angles in spherical geometry. That comes from what we mentioned earlier, that the sum of the angles is greater than 180 and less than 540. So it's possible to have 3 right angles in our spherical geometry for a triangle. We have a few more formulas. These are based on the same figure I showed you on the previous slide, where you don't necessarily have to have the right angle. We have the spherical law of sines, this formula here that I'm pointing to, and then there's the spherical law of cosines, this formula here, and there's a whole bunch of these formulas. I just shown you a couple of them, just to make the point that we can do trigonometry on a sphere, and it's been well developed in the literature. There's a Wikipedia article, I'll give you the link to this, called Spherical Trigonometry, and it has an extensive list of trigonometric formulas for triangles on a sphere. All the great circles which are perpendicular to a given great circle meet in 2 antipodal points known as poles. I have an example here. So we have a great circle A, then these other great circles going this way, B and C being 2 examples. So you have a 90-degree angle here where they meet. All these great circles that are perpendicular to A meet at poles in the figure that's N and S. In terms of visualization, it may help to think of A as the equator on a globe, and the great circles perpendicular to A as being longitudinal, also known as meridian lines, and N and S being the north and south poles. So, of course, we could have a different great circle going, in another direction, and then you would have different north and south, or whatever you want to call them, antipodal poles corresponding to that all the perpendiculars to that great circle. Just a note here, these lines going this way are not great circles. I would have preferred not to have them in the figure, but I was reusing some clip art, so I just left them in here. But just focus on the lines going up and down, and then this great circle here at the equator. Let's talk about the single elliptical geometry. It's very similar to the double, except that we cut the sphere in half is shown in this figure here, and then we make some modifications. This is known as the modified hemisphere model. Each pair of antipodal points on the boundary, so C here and C here, are considered to be the same point. That's why I use the same letter here and here, and for B and B and A. They're considered to be connected directly. So that's kind of the modification. In this model, semicircles are effectively converted into closed curves, known as modified curves. So we have one A, or two actually, A and B. So from C to E and then back down to C. That's one modified curve, and that's a straight line. And another straight line would be B, going from C up to the top of the hemisphere down to the same point C. So there A and B are two straight lines. We have a few more here. A, so A, E, then all the way down to A, that would be another one. CEC, we already talked about CEC. ACA, so ACA, so that's along the boundary, and then CFC, we already talked about that one. In single elliptic geometry, two straight lines intersect at one point. We can see that here was A and B. They intersect at this point C. Again, this is the same point. They're considered to be, you can think of them as kind of being joined directly. If we did not make the modification to the hemisphere model, equating antipodal points, that is, some pairs of straight lines would have 2 points of intersection, and others would have only 1 point. So for example, A and B, which I just mentioned, would have 2 points of intersection if we didn't equate the two antipodal points. Whereas A and C being this one here, and A here, they would just have 1 point of intersection. That would be the point E here. Assume the radius of our hemisphere is of measure r. The boundary of the hemisphere is a circle. We know that. Its circumference is pi r rather than 2 pi r, since the boundary is completely traversed by going continuously from any point on the boundary to its antipodal points. In other words, going from A to A covers all the points, because each one of these points between A and A here are the same point on this other side. So that's kind of a bit of a wrinkle to the model. The boundary is also considered a modified curve. The other modified curves, being semicircles, have circumference, or more precisely semi-circumference, pi r. So these have pi r. So this little modification we made here with equating antipodal points makes it such that all the straight lines have the same circumference, same length, pi r. We have a few more properties concerning our model, which I'll mention here. The shortest path joining 2 points on this modified model must be an arc of a modified curve. So for example, the shortest path between D and E is on an arc between A and A. In other words, on a straight line between A and A, or semicircle. And this path between D and E is known as the geodesic arc, same term that we used in the double elliptical model. Through each point, there are an infinite number of modified curves, or straight lines, the totality of which cover the entire sphere. So you can see this here from F. If you took all the different curves going through F, that would cover the entire hemisphere. You may want to try to visualize that for E. It's a little bit harder to see for E or D. Through each pair of points, there passes a unique modified curve. So you pick any 2 points and you're going to get one modified curve going through them. A pair of modified curves always meet at a unique point. So we can see that for the ones that are not meeting on the boundary. For example, we have the curve here, C, going from A to A, and the curve here, B, they just meet at one point. And then the other curves, like the A and B, meet at one point because of this modification where we equated antipodal points. We have a few more properties here. A pair of points are said to be opposite if they divide the associated modified curve, i.e. straight line, into equal parts. So in the figure here, A and F are opposite points, A and F. So we have this modified curve C, script C, and F to A and F to A is the same distance. So the A and F would be opposite points, whereas A and D are not opposite points since they don't divide their modified curve in half. Conversely, if a pair of points divide their associated modified curve into two equal parts, then the points are opposite. So that's just completing the definition of opposite points. Opposite points are joined by exactly two geodesic arcs of the same length, pi r over 2, and non-opposite points are joined by exactly one geodesic arc. And that's because we define geodesic arc to be the shortest distance. So, for example, E and D are not opposite points. They have one geodesic arc between them, this one I'm pointing to. There's another one, D to A to F, but that's A to E, excuse me. That's longer, and we define geodesic arc to be the shortest path. So by definition, this other one, D to A to E, is not a geodesic arc. That was the same definition we had in our double elliptic geometry. The maximum distance between 2 points on the modified hemisphere is pi r over 2, where r is the radius of the hemisphere. And then this last one's a little bit hard to see. I'll give you a couple of examples. All modified curves perpendicular to a given modified curve meet in a unique point. So if we take this modified curve from A to B to C to A, this one here, then B, script B, this modified curve is perpendicular to the boundary, and then we could rotate this slightly and go from, say, B to F down to B, and that would also be perpendicular, and you can go from here to here to here and so forth. So all of those curves perpendicular to the boundary would go through point F. So that's one example. That's probably the easier one to see. Another example would be if we take the modified curve B, script B, from C to F to C. What are all the modified curves perpendicular to script B look like? So one would be here, C, A, C, right? That's perpendicular. And I've drawn a few more. Here would be another one. So this is a right angle in here. This would be yet another one. This is a right angle. And you can see more of them going this way and then on the other side. So they would all meet in a unique point, and which would be A in this case. You may want to see or try to visualize what all the modified curves perpendicular to, say, A, this one from C to E to C, what they look like. That's a little even harder to visualize, but it would be a good exercise in visualizing geometric shapes. Triangles can be a bit strange in our hemispherical geometry. I have an example of two triangles, which I'll show you here. So the first one, I'll call it T1, and it has sides ADF, AC, which I labeled as X here, and CEF. So that is a triangle. And that's kind of not too weird, but the next one is strange. So T2, let that be the triangle CEF AC, the same as this AC, except it's on the other side of the boundary, and we'll label that as Y. And then AF, this actually this one here, A to F here. So this side, and this side. Draw it in red. So that's a triangle, believe it or not. You notice you're going from A to C, and then C to F, and then F back to A. So it's kind of distributed. So that's weird, but it's a triangle. And it's even more strange is T1 and T2, these two triangles, have corresponding sides of equal length. So they're actually the same sides, right? AC and AC here. They share this one here, and then the other one, F to A and A to F, assuming A is and F are opposite points. In other words, they subdivide this modified curve here from A to A. Then the sides are all the same, and normally that would be in Euclidean and hyperbolic geometry. That would imply that the two triangles are congruent, but that's not the case here. And the reason is that the angle here at CFA is not the same. It's pi minus alpha here in this triangle, the red triangle, and it's just alpha in the triangle T1 that we defined first. So the two triangles are not congruent, and that's strange, but that's the way it is in our hemispherical geometry. Then one last point in this lesson, not really related to this, but I don't have anywhere else to put it. The triangle inequality that was mentioned for spherical geometry also holds true in hemispherical geometry. Okay, so that's the last lesson in the series for non-Euclidean geometry. I have another somewhat related series of lectures on topology, which come back a little bit later on in that series to this hemispherical model. It's related to something called the projective plane. And then I have yet one more lecture series on complex analysis. So if you're interested, I have quite a few more lessons for you to view, but not on this particular topic.